All right, welcome back from Thanksgiving break. Um, so nothing new today, just the final exam review. So just a couple of reminders, course evaluations are out. There's a link there if you're interested in filling those out. There's also on Canvas in the top left corner, there's a link, I think just under home and maybe the search, it says course evaluations. So it's another shortcut to get there. Today we've got our final exam review. Due Wednesday at 11:59 p.m. are the presentations, a video upload to Canvas, and the report about the video upload. If you actually go to the video upload page and click on that, I actually have sort of a, if you're having trouble figuring out how to structure it still, there's a couple suggestions on sort of the general flow that might work for you for your video. So you could go there. You don't have to be on camera. It can be just an audio overlay on top of some PowerPoint slides. I would recommend using the instructions at the bottom of that video, the page for the assignment though, where I talk about using Zoom. So if you, even if you're all out in the same place, you can all connect to one room in Zoom, share a screen, and have one person move through your slides or whatever your visuals are. Your visuals might be, actually going over into Arena and running a sim and then coming back to slides or however you want to do it. But you can have one person driving that, sharing their screen, the other is connected. And if you record that, which you can do to the cloud or locally, then you can get everybody participating even if they're not in the same room. So that's just one. But if that doesn't work for you, if you just want to do video overlays on top of the slides, that's fine, but try to upload it in a video format that is easy to digest on Canvas so that during the peer reviews and the grading, you don't have to download something and then open it up in PowerPoint or something like that. So the expectation is that it's a video upload. How you put that video together, there's a bunch of different ways. Also, there's no requirement in the rubric for every team member being equally represented in the presentation. It's going to there will be some teams where some team members did more of their data collection, some did more of the modeling, and some did more of putting the presentation together. And although it might make sense in most cases for all 4 team members to participate, that's not something that is a strict requirement. So just kind of make it flow, make it compelling. So that is due 11:59 Wednesday night. Same thing with the report, which is this 4-page report. Make sure that you pay attention to that format. It makes it easier for us to grade if things are in the required format. And both of those have this hard deadline, 11:59, because because the peer review process synchronizes everything so that I can only issue the peer reviews once all of the assignments are in. If an assignment isn't in and I do the peer reviews, then people don't get assigned. So that's why it really has to be in. There's no a grace period. It's a little confusing though, because the way Canvas does the peer review, the assignment looks like it's open. So it will look like it's available, but that's because in order for the peer reviews to work, I have to leave it available for that peer review mechanism to still work. So it says it's available, but that's why I'm emphasizing, and I'm going to probably send emails out as well, that it really is this 11:59 deadline so that the peer reviews can get assigned, and because then that's a synchronous process. So that's that. And then Saturday night, so everybody, after you submit that, you'll get a assigned report to read and a presentation to watch that won't necessarily be from the same group, but it'll be from a group other than your group. And then so watch that presentation, fill out a rubric, and leave some comments, read the report, fill out a rubric, and leave some comments. And then once those are submitted, then you'll get your peer review credit. Those peer reviews are due Saturday night. And then so that's the schedule for the project. And then otherwise for the exam, I'm still writing the exam, but it should become available. So theoretically tonight around midnight, it might be plus or minus, depending on, I'm writing this exam, an exam for another class. So depending on how those come together and if there's any bugs in the Canvas implementation, they need to be ironed out. But nominally, tonight around midnight, the exam should become available. Stage 1, as I mentioned in an announcement, I was originally going to make it Wednesday, Thursday, Friday, and decided to just go, why don't I just make it Saturday, Sunday as well. So stage 1 is starting this week, so tomorrow, Wednesday, Thursday, Friday, Saturday, Sunday, and then it disappears Sunday night. And then stage 2 will open up basically finals week, Monday, Tuesday, Wednesday, Thursday, Friday. So I may end up fuzzying the Sunday night transition between them. So maybe stage one will have a little bit of a grace period into Monday morning, and then stage two will have a little bit of a delay because I doubt people will be rushing to start stage two in the middle of the night, Sunday night. And then that just makes things a little bit easier for those trying to, who maybe started a little late. But hopefully that relieves a little bit of the pressure this week because I know you've got this, this project, and I'm sure other things are going on in your other classes and such. So, so that's the plan: Wednesday through Sunday for stage one, and then stage two that'll be during finals week, and you'll just basically get it Monday through Friday, all of finals week. Okay, so any questions about the schedule? All right. So just as reminders for, there is a specific format for your report. And so that's that 4-page report, expecting to have these sections. So the 4 pages are these sections here. So your title page doesn't count. So then you've got 4 pages to do this. You don't have to put your entire arena model into those 4 pages. You should just highlight the things that help make your points. And then anything else that you feel is necessary for it to be complete, you can have an unlimited appendix to put that into. But anything you put in your appendix, make sure you reference. So it's great if you use figure labels. So you can say figure, for more details, see figure A1, and then that will be in the appendix. So if there's just things in the appendix that aren't referenced, then I'm not going to read them. So because I don't know what they're supposed to speak to. So even though they might be in your unlimited page appendix, you still have to reference them if they're relevant. So, but the bulk of your argument should be in these 4 pages here. And this executive summary should be an abstract of the entire report. So the key result that you find, and it's fine if your key result is that you tried a new process and it was worse than the existing process, or it wasn't any significantly better than the existing process. That is a fine result. There's nothing wrong with that. But then state that in your executive summary, and then of course in your results here. So that's the report. Any questions on the report stuff? Okay. And then, like I said, the presentation, I've got kind of a similar layout that I just added in yesterday, just for some extra help or hints. So if you go to the presentation submission page, then I've got kind of a suggested, it's not required, but a suggested flow for that presentation, which kind of walks through kind of a similar idea where you explain the problem, you explain the motivations, the problem, the model you use to address the problem, and then you analyze the results and then give some conclusions. So kind of a similar idea. All right, so any questions about that admin stuff before we switch to exam mode? Okay. So exam, it's the same format as the midterm. It's the same length as the midterm because theoretically it's meant to fit within a normal class period because stage one is theoretically given during a normal class period, but it's all Canvas-based. The availability is longer than a day. So again, if you didn't hear that before, stage one will be available Wednesday, Thursday, Friday, Saturday, Sunday. And stage two will be available next week during finals week, Monday through Friday. And so all Canvas-based, you don't have to come here. I will be here Thursday at the normal class time. So if people want to come here to have a quiet space to take stage one, bring a laptop, that's fine. If nobody shows up within the first 10, 15 minutes, then I'll probably leave early. So, and then stage two, I'll be here. I think it's on Canvas during the period that we've been assigned this classroom. I think at like 9:50 a.m. or something like that, or 9:20 a.m. Again, the time is in the Canvas calendar. I'll be here during that time in case you want to take the collaborative portion here, just like in the midterm, but you don't have to. You can take it elsewhere. It's totally up to you. But this space I'm just made available so you have a quiet space or a space that everybody's got on their calendar in case you want to meet for that collaborative portion. So there's two for stage one, two-sided handwritten. So I say handwritten, I mean hand produced. Just like with the midterm, it's okay if you type it, it's just not screenshots. So formula sheets, that's kind of what I'm saying here. And then stage two, just like the midterm, open book, open notes, open Canvas, and you can collaborate with other students in the class. You can do that over Slack. If you've got Discord channel as long as nobody outside the class is in that channel as well. That's fine. So there's a little bit of an honor system here, but the idea is only collaborate with people currently enrolled in this class. So same as the midterm. It's going to be cumulative, so across, but most of our, like the first and second half of the class are meant to kind of fit together. So, I'm not gonna. We talked about chi-squared tests before the midterm and after the midterm, but we just kind of generalized them after the midterm. So by asking you about chi-squared tests about general distributions, I'm sort of covering both things there. So there's not a lot of totally different things that happen before the midterm. I want to make sure. I mean, the biggest thing is I want to make sure you know the simulation basics. So what entities are, what activities are, the difference between activities, delays, those sorts of things. I want you to make sure you can do a hand simulation, those sorts of things. I want to make sure you know some probabilistic models, like which ones are best to model which things. But we kind of talked about that after the midterm anyway, too. So a lot of the stuff after the midterm was just taking the pre-midterm stuff and extending it. So it's cumulative, but you're going to see it's primarily biased towards discussions that we've had post-midterm, except for maybe some leading questions about some simulation basics. So this is, these are the things that we've covered. So, this kind of list, if you go through this list and you feel like, you feel like you could defend against questions against these sorts of things, then I think you're in good shape. One difference between the midterm and the final is I will have some questions referencing ARENA a little bit, so do expect to see, and you can look, I've got final exam samples online. There will probably be some diagrams from ARENA where I'll ask you about certain blocks. Where might you, I might say, in a previous finals, I would say, well, they wanted to change the way queues were handled. Which block would you expect them to adjust in order to make this change happen? That sort of thing, and then give you a bunch of options. So those sorts of questions do expect to see a little bit of ARENA on the final exam. So that will be there too. So see some diagrams. So there will be, there's going to be a lot of multiple. So it's a Canvas-based exam. So it's just like the midterm. You're going to expect to see so multiple choice tests. You're going to see matching problems. You might see a couple of formula problems where you'll get random numbers, for your test relative to other students, but you'll still have to go through the same process. There might be some, one-ish design problem, maybe divided across 2 or 3 questions. So, designing or making sure that you understand how to design a random variate generator, or seeing if you understand. So what I like to do for the final exam is blend the design problems with some of these variance reduction technique stuff that we talked about. So the variance reduction techniques, like common random numbers, antithetic variates, we leverage random number generation in order to make them work. So as you'll see, if you look at some of my final exam samples, sometimes what I like to do is take a random variate generation problem like you'd see at the end of the midterm and make it so that instead of generating just a general random variate, you might be generating an antithetic variate. So you'd have to know that, okay, I need to grab 2 random numbers, generate 2 variates with each one of those random numbers, and then sum them together and take an average in the way that antithetic variates does that. Or common random numbers, common random numbers, I might have to run the same random number into 2 different inverse CDFs and then get 2 different random numbers out of that. So it sort of makes sure that you not only know how to do inverse transform sampling, but you are able to apply it to one of these variance reduction techniques. So that might be a way that I would blend those things together. So, for practice at this, like I said, go into the final exam module. I've got a bunch of final exams from the previous semesters that are there. There is a practice Canvas exercise. Looking back at the homeworks is a good idea. There are some additional problems I've posted with solutions of some of these that are also in there. So there's a bunch of different resources. And then when you look through the modules, if you need additional help, or just want to hear it in a different way or read it in a different way, then every lecture is associated with a chapter in the textbook, which speaks to those topics as well. So, so those are the major overview of the, what's going in the final exam. So I think the rest of this, yeah. So I don't have to do any of the rest of this, but this is, if no one has questions, I can go through this until there are questions generated. So the rest of this deck is just the greatest hits from the whole class. And so starting from the very beginning, what are models, all the way down to the variance reduction techniques and some arena stuff. And so, again, if there's no questions, I can go through these things. And then when past questions come up, they don't have to be about the things I'm going through. Then I can stop and handle that. We can work problems or whatever. But that's all that I've got for you. That's basically the rest of this. So are there questions that I can handle? Okay. I'll give it a couple of seconds here. All right. So if there are no immediate questions, then a couple of things. This time is for you. So I'm not going to do a clicker today. So if there's nothing else that I have to say that's useful to you, you don't have to sit through me being here. But otherwise, I'm going to just walk through these slides. And as questions come up, again, they don't have to be about this. You just gets your mind, jogs your memory. Then just raise your hand, and happy to take those. So as a reminder, so go back to the beginning. I could definitely ask, basic questions about what are models. Remember, a model is a what if question. I could definitely ask you, definitely know these definitions, these fundamental definitions. So entities, state variables, events, activities, delays, and so on. So again, all of these basic content grammar that you need in order to just talk about a simulation. Know how to do a hand simulation. And by the way, now that we're all experienced in hand simulation, if you've looked down or looked in Arena, there's a little step function here where you can actually have Arena step through this table. And so, now you know what's going on behind the scenes. And so you know that if you wanted to pause your simulation and then have it step event by event, you can click that and it'll go event by event through your simulation. So, so you know how to do that. So hopefully you know how these different inputs then factor into these tables. So these inputs are activities. So, in a queuing node like this, those will be like interrival durations and service durations. Those are the things we know ahead of time. And then we run the sim to figure out the delays, which we don't know until we run the sim and see how things match up. And so, know about all of that. Then we moved on to probability. So, our models are stochastic models. So they use probability distributions to provide variation, which makes it easier for us to build realistic models without having to put a lot of extra parameters in. So we have to know about probabilities. So, know the difference between a PMF, a PDF, a CDF, know the difference between expected value and standard deviation. Those common distributions that we've talked about, I think I've got a cheat sheet for some of those in maybe a slide or two. Know the common parameters, like know that an exponential only takes one parameter, a normal distribution takes two parameters. Know the difference between an exponential and a Weibull, that you've got that shape parameter that allows it to be more flexible than an exponential, similar with an Erlong distribution. So, those common cases there, know about those. This general idea of input modeling and how probability fits into that is important. Here's that kind of cheat sheet. These are the distributions I'm kind of expecting you to have as your kind of probabilistic vocabulary, so that you're familiar with these discrete and these continuous, the discrete and continuous. And then, know that there's this thing called a Poisson counting process or Poisson process that links together the counts, Poisson counts, under discrete with the exponential interarrivals under continuous. So know how those two things are related. That's important for a lot of these processes. Here again is a cheat sheet. If you need to go back and then see a quick summary of when you use each of those continuous and each of those discrete, there's one provided there. Any questions so far from these? Just reminders of stuff from the early in the class. Okay. I might ask you to generate a random number, to use a linear congruential generator, an LCG, to generate a random number. It's more important, though, for you to kind of know how, just in general, the process that there is a mathematical process to generate uniform numbers, that then we go through a transformation process to generate random variates. And that's how we get a random variation. And we can then co-opt that with variance reduction techniques, and knowing how that all plugs into that. So that will be the kind of more critical thing to keep in mind for this. And so knowing that there are seeds behind the scene, that's what allows us to, knowing that the reason why we can trust that replication 1 is independent from replication 2 is because ARENA used a different seed in the beginning of each one of those replications. Understanding how that works is important. Again, it's probably, it's not a bad idea to remember the LCG formula. This is something that I just want you to know that's out there, that exists as a good way to generate uniform random numbers. It's not, I wouldn't prioritize it. It's not going to be a major part of the exam. That's more the midterm. Inverse transform method, definitely understand this diagram. This is a critical thing coming out of this class, is knowing how you can get from uniform numbers to random variates. And the inverse transform method is 90% of the time is the way we do that. And so I just walk through the inverse transform method there as as reminders. All right, so that basically brings us to the end of the midterm. And so everything from here on out will be everything after the midterm. So definitely stuff that's with fair game for the final exam. So we talked about a lot of statistical topics, a lot of stuff about classification, about false positives and false negatives. And hypothesis testing. And so, understanding this diagram here, how does this diagram relate to hypothesis testing? Where do those 4 categories come from out of this diagram? Where does this threshold come from? What is the ROC curve? And what is the trade-off between type 1 error and statistical power? Those are good things to have conceptualized to be able to answer questions about. And so just some hints there. Know what it means to reject the null hypothesis. And so, sometimes we want to reject, I say want, so how do you determine what it means to detect the difference from the null? So is that, there's some cases where detecting a difference is something that is as a positive result, that it shows that okay, so if I've introduced a new way to do something in a manufacturing system, then I want to be able to detect whether my manufacturing system's new way is different than the old way. So that's maybe a positive result there. But then there are other times when you're trying to validate your input models. In those cases, if you actually want things to be the same. And so in that case, detecting a difference suggests that you need to recalibrate. So there are different ways, sometimes detecting a difference from the null indicates that you have a result that you should bring to your stakeholders right away, because you've now detected that there's a new way of doing things that might be better than the old way. Other times, detecting a difference for the null tells you that you need to reshape your model, because you've now detected that the inputs you've used are different than the inputs for the real system. And so now you need to reshape the inputs in your model. So, knowing that, there's not one way to interpret rejecting the null. It depends on the context. So being able to interpret that statistical result and turning it into something meaningful. Understand statistical power. I thought it was great to see in some of the discussions with groups that have come to office hours and so on, that some of you really are trying to like choose a number of replications for your sims that are they're not arbitrary, that they're actually bringing confidence intervals to particular sizes and so on. And so understanding that idea that it's not arbitrary how many replications you choose, that sometimes you need more and here's why, and sometimes you're okay with less and here's why. And understanding how these things all fold into that discussion is a good one there. And then likewise, knowing how variance, how noise in your system, how that affects, how that becomes a challenge for these things. And so, what is the confidence interval? What is the prediction interval? How does it vary with replications as well as just general noise in your system? So good things that we talked a lot about, this after the midterm. Questions about any of this so far? Anything you want me to go over? Okay. So input modeling, being able to look at a histogram, knowing the difference between, like being able to spot an empirical CDF and knowing how that's different than a histogram is a good thing to know. Knowing that, how the different the challenges in choosing the width of histogram bins, being able to sort of spot like, oh, that's a good histogram, that's a bad histogram, and here's maybe why. Knowing the difference between discrete and continuous data and how that changes your choices downstream when you're doing your input modeling. So, I think in looking at some of the input modeling reports, then sometimes we get into this issue that, if you get a bunch of count data, you don't just want to go into Arena and say fit all, and it might fit like a gamma distribution to a bunch of count data, knowing why that doesn't make any sense. Because if it's count data, then it only should be counts coming out of it. So really, the input analyzer may not be able to help you that much because it only has one discrete distribution, Poisson, and maybe that's perfect for yours, but maybe not. And so maybe in that case, you have to use an empirical distribution just to get the probabilities for every outcome. So knowing that, that idea that they're completely different worlds, discrete and continuous, and they require a different way to fit your distributions. Being able to understand a QQ plot and a PP plot, being able to look at one and sort of, I'm not gonna have you process a QQ plot. Like I mentioned that in practice, there are rules for how, if things are misshapen in a QQ plot, if they vary from linearity, then how they vary tells you which direction to go in to pick a new family. And that's what you do in practice. I'm not asking you to memorize all those rules for the final. So just know, that a QQ plot exists. Know that you run a QQ plot before you have parameters to get the families. And then after you've done a goodness of fit test for particular parameters, then you can do a last gut check of your, last sort of validity check by doing a PP plot. And if you've done a good job with your goodness of fit, then hopefully your PP plot at this point is also going to be linear. So QQ comes way early, the PP plot comes late, and the goodness of fit stuff and the parameter fitting, the maximum likelihood estimation, that goes in the middle. So again, this is just the discrete and continuous ones that I'm hoping that you'll know. Know how to read this disk line from Arena. So know that the disk encodes the inverse CDF or the quantile function. That's why you get the CDF first and then the outcome second. And this is just a common way that you often encode discrete outcomes into simulations by putting either their CDF or their inverse CDF. And so with Arena, it's the inverse CDF. So just know how to read that, because I could give you, you can see in previous final exams, sometimes I will ask a question where the information about the distribution is encoded inside a disk. And so you have to know to read that in order to process the rest of the question. So knowing how to interpret that is good. I'm not going to go through all of these, but this is just a cheat sheet for those common distributions, what they look like, how many parameters they have, what they're used for. So there's like the normal, the exponential, the Weibull. So those are three of the really big continuous ones. Poisson, a really important discrete one, and how does it relate to the exponential? And then here's the QQ plots. There's a histogram here. I can't really tell the difference between these possible PDFs. So then I do a QQ plot, and then I can do a PPP or a PP plot after I fit the parameters. How do I fit the parameters? We talked about, well, you start with summary statistics because those will probably be useful. But once you've got the summary statistics, then you'll use maximum likelihood estimators as one way to provide the best parameters for each one of these distributions. And they'll probably be functions of these summary statistics. Know that whenever you calculate a variance, you burn a degree of freedom because you have to use an estimated mean in order to estimate that degree of freedom. So a lot of those t-tests that we talked about, some of those degrees of freedom that you saw, like those expressions for degrees of freedom for those two sample t-tests that we went over, those come from these standard deviations burning a degree of freedom because they have to use the mean this way. So remember that n-1 is in there. You don't have to, this table is just in there as examples for estimators. You don't have to know this table. I wouldn't put that on your cheat sheet. It's not that important. Chi-squared test. So know how to do a chi-squared test for a general distribution. So the big difference between this and a uniform distribution is you have to calculate the expected outcomes for every bin. Know that you also have to regroup bins together. So if any of the bins have an expected count less than 5, then you should find an adjacent bin and group it with that until you get a bin that has 5 or greater. And then you use that. So you're gonna produce less and less bins as you move toward this requirement of the expected count being greater than or equal to 5. So you want to use as many bins as possible, as many classes as possible, while still meeting that requirement. And then once you have your bins, then you can figure out what's well, you should know just by adding them together what the expected count is in each bin, and then you count how many observed things land in that bigger bin, and then you can calculate your chi-squared. So the chi-squared larger is farther away from the null or farther away from the hypothetical distribution. So you could say larger is a bigger difference. So the critical value in the back of the book is the maximum allowable deviation. I'll give you all the critical values, just like on the midterm. I'll give you a t-table, a chi-squared table. I'll give you standard z critical values. I'll give you the KS test critical values. So same as the midterm, I'll give you that at the top of the test. So that will be available. The other thing about chi-squared tests is this degrees of freedom. Every time you estimate a parameter in your hypothetical distribution, you burn a degree of freedom. So you automatically burn a degree of freedom just because there's a slack class that, because you already know how many data points you have, then once you know n-1 of your classes, you immediately know how many are in the last class. So that's where the n-1 comes from. But then once you also estimate a parameter, like, I'm trying to see, is this a good exponential fit? Well, I don't know what the parameter for the exponential is, so I'm going to fit it from the data. Well, at that point, you burn another degree of freedom. So know that the degree of freedom you look up has to do with the number of bins you pick and the number of parameters you estimate. So that's another key difference. Any questions about these setups for the chi-squared, the generic chi-squared? Statistically speaking, know that chi-squared is very different than like a t-test in that a chi-squared is you're comparing distributions, so predicted distributions and expected distributions. So it's a test for counts. So how many, it's not necessarily testing a discrete random variable, but it ends up comparing discrete counts to expected counts. So that's knowing that count relationship is an important one there. Also, then a alternative for the chi-squared is the KS test when you have very little data. So you need a high-powered test because you have very little data, and a chi-squared test, you can't meet its constraints. So the KS test, the key thing here is you sort all of your data, and then you plug it into the hypothetical CDF. So the CDF that you think it might be, and you're testing to see that you're testing that hypothesis. And then you take those hypothetical CDF values, which will be sorted because it's a monotonic function. So you've already sorted the data. So when you plug them in, the CDF values will be sorted. And then it looks just like what we did before the midterms. So you've got your sorted CDF values, and you calculate the intervals of where you would expect those to be if it was a good fit. And if it was a good fit, then basically this should be a uniform distribution. That's one of the keys, is that if you draw samples from a distribution and you run those samples back through the CDF for that distribution, then the outputs of that CDF will be uniformly distributed. And that's what the KS test is testing. So you've transformed your samples by what you think is the CDF. And if it is the CDF, the output of this will be uniformly distributed. So we're testing to see, does this lowest CDF value, does that fit in the lowest uniformly distributed bin? So all of these things, 0 to 0.2, 0.2 to 0.4, those are just the interval from 0 to 1 cut up into bins based on the number of data you have. So if you have 5 data points, 5 bins. You have 10 data points, 10 bins. And you would expect then the CDF to land in the bins in the order in which they come. And so, there might be slight deviations. So some of these might fall outside or right on the edge of their bins, but they should be close. And so you're measuring the distance between the CDF and the bin it's supposed to be in, and that's the critical statistic that the KS test tests for. So in the back of the book, there's the degrees of freedom, or the number of data, which are the number of bins, but it's not like the chi-squared. So there's no additional binning that goes into play like in the chi-squared. And both the KS test and the chi-squared test, that you use the significance level directly. You don't divide it by 2, because there's no two-sided version of these tests. There's only a positive difference. And so there's only a one tail. So there's only one side of it. And so you don't do 0.05 divided by 2 like you do with a t-test. Any questions about the chi-squared or the KS test? It's good to know how to do those tests, when to use them. There are other tests. Just know that they exist. I'm not going to ask you a great deal of details here, but the key point that I'm bringing up with these is that these additional tests generally are going to be higher powered tests. So high powered tests are great for goodness of fit tests if you really want to ensure that you have a good fit. So if a high powered test does not reject your data, then it is very likely that your data actually are the hypothetical distribution. If a low powered test does not reject your data, it might just mean that you don't have enough data. So we have the Anderson-Darling is a popular high-powered generic test. And then there's even higher powered tests that are distribution specific, like this Shapiro-Wilk, where in so many of our stats, we require data to be normally distributed before we're even allowed to do the tests. So like a t-test, you need normality. In ANOVA, you need normality. And so it's really important to see if your data are normally distributed. So that's why we need a high-powered test for testing normality, even when there's very little data. And that's why we have these distribution-specific tests. So understanding that general philosophy is what I want you to get out of it. Is that, when do we need more power? Why might we want a distribution-specific test? Knowing that this is a popular test for normality and this is a popular generic test, I'm less worried about, but I'm just putting those up there as examples. All right, any questions? Okay. Then we did TV and V, testing, verification, and validation. So the idea behind verification, that's debugging your code. Hopefully now that you've done your final projects, you can see, you can kind of feel the difference between verification and validation. Like sometimes you just notice that your sim isn't producing results that are anywhere what you expected, and you realize it's because you used an arrival process that had a different unit than your service process. And because one was in minutes and the other one was in seconds, then you weren't getting the results you're expecting. That's verification. That's fixing those bugs. But once they're all fixed, then you might get a result that's different in your sim system from your real system. And then you go in and say, well, oh, you know what the problem is? Our real system had this other process that we didn't think was important, but it turns out it's really important. We need to add that process to our model. That is validation and calibration, the idea of augmenting your model to include more reality in it. So that process there. So V&V and calibration. So what we talked about there, validation is a kind of goodness of fit. It's the goodness of fit of your model to the real data. So you had goodness of fit of the input models, but you also have goodness of fit of your model, your simulation model itself. So you can do statistical tests to say, does the mean coming out of my simulation model, is it anywhere close to the mean coming out of my real world model? And that's why you might do a t-test or a test of means out of that. It's rarer that you're going to expect the distribution coming out of your simulation model to match the distribution in the real world, because the real world probably has other effects in it that you've chosen to exclude because you're trying to get to some core generalizable principle. So that's why we might test for distributional fitness, like goodness of fit and distribution on the input side. But on the output side, we might only care about, do they match in the mean? But remember, when I say match in the mean, that's including the confidence interval, including the uncertainty coming out of your sim and the uncertainty coming out of the real world estimates. So that's important to keep in mind. And then performance. And so now we're at almost the back end here. So we will, before the end of this class period, we will cover everything we've covered in the entire semester of this course. So we didn't cover a lot. It felt like a lot, but we can pack it all in to these couple of slides here. So now that we've built our simulations, now we have to say, how do we actually measure performance of our sims? We talked about point estimators, but we talked about how we're trying to move from point estimators to interval estimators because there's uncertainty. There's just intrinsic uncertainty about your systems are noisy because they've got random variables in it. And so every time you run your system, you might get lucky or might get unlucky. It may not be a typical output. So you have to run multiple replications of your system and create a confidence interval out of them. So your estimates are intervals now, not points. So that was an important thing. So what are the two intervals that we care about? Confidence interval is the big one, and then prediction interval is also, I haven't stressed it very much in this class, but it becomes very important in other applications. So, because if you're trying to plan, it's good to know. In the case of confidence interval, this is more like understanding that, if I'm estimating the average wait time in general for my system, and that's useful for operations research. But for planning purposes, the prediction interval becomes helpful because you might want to know, like, how bad could it be? What's the worst wait time I might be able to get? And the prediction interval gives you a better idea of how, if you have this much data from your sim from these past 100 replications, then how bad could the wait time be, the average wait time in the next replication? And that helps you, maybe plan for risk. And so that can be a helpful tool. But confidence interval is whenever, like, we've moved now to a bunch of different types of confidence intervals. Those are all behind the scenes, just different types of t-tests. And so, the t-test seems kind of academic. It seems sort of, it seems kind of esoteric. It doesn't seem like it's the best way to communicate to a stakeholder. And that's right. I mean, it's a weird thing to bring up. So instead, we package a t-test into a confidence interval. And the stakeholders, they can better understand, or at least think they understand, the confidence intervals. And then you, as statisticians, as quantitative people, should then know that when you interpret a confidence interval, that confidence interval is just a t-test. So it's just a way of saying how many hypothetical parameters could I reject with a t-test and how many can I fail to reject with a t-test, all into one compact interval. And so every time you do a confidence interval, you're doing a statistical test. You just aren't calling it that. So that's one of the nice things about it. So once we were done with intervals, and then we talked about the two types of simulations, transient simulations for terminating systems, where the key question was how many reps, how many replications, and we came up with this formula, and this was an alternative to doing a power analysis. And so understanding where this formula comes from, why we use it, how the general process of running a couple of pilot runs to get a variance estimate, and then using that variance estimate to then predict how many more replications you need. Again, it's great to see some of the groups doing this in their own final projects, and following that logic of saying like, I noticed that we get a lot of variance in our queue lengths or whatever coming out of our sims. And we thought in order to really be able to say something compelling in our presentation, we'd want the estimated queue length to not vary by more than 2. And so then, so how do we know that, how do we get that to happen? Well, then we plugged into this little value here, and it turns out we need to run 300 replications to get a queue length that we can estimate within that error bounds. So, and then that makes for a much more interesting argument as opposed to, in your presentation saying we have a giant confidence interval where our average queue length is anywhere from 1 to 150. That's just not a valuable result. And so saying, well, but our average queue length is anywhere from 49 to 51, well, that's much better. So being able to recognize how to go from how to make the argument to how many replications to run is an important one. So it's a good thing to have. And then we talked about well, what about steady state estimates? So a lot of you are doing steady state simulations in your final projects. And that's because you're just, for convenience reasons, you didn't want to gather data all day at a bank or at a restaurant. So you just really wanted to focus on and it makes sense for this project. It's a short project. You don't have much time to do it. So you're really going to just focus on the busy period at the restaurant. And so you're not sort of studying the restaurant as it opens and as it closes. You just want to know, what is the kind of steady state value within the middle of the busy period. So you're doing a lot of these steady state simulations, which means you not only have to worry about how many replications to run, but also to make sure you've got a warm-up period where you get rid of your system. You might be simulating the busy period of the day, but when you start that system, your simulated system is not busy. It's like you just opened the shop in the simulation. So you have to wait for your simulation to reach that busy period and then start taking data. So understanding this idea of your warm-up period, if you have the ability, and this is a little beyond some of the stuff we've shown you how to do in Arena, but it is possible in Arena to warm start some of your initial states, your state variables inside your sims, and that's an alternative to this warm-up period. But for your final project, you'll probably just do a warm-up period. So, and then, more replications or longer execution time. So if you're just studying the steady state, rather than saying, I'm going to run 1,000 replications, you could just run one really, really long replication that gets batched in Arena into multiple little batches that each one of them has an estimated performance. And that's something you can do in a steady state sim that you can't do in a transient. So understanding those issues there. And then relative performance estimation. I've mentioned to several groups for your final projects that with when you're for a very short project like this, where you're going to have simple models where they're not very calibrated, like you just don't have the time to do that high, those high degrees of calibration. I'm expecting your models to be off relative to the real performance in the real world. And so because of that, I'm expecting you to do more relative performance estimation. So saying that I'm going to create an as-is model of my system and a propose change to my system and compare the two simulation models, and then trust that differences in my simulated world from as is to proposed reflect a possible difference that I'd see in the real world. So that's what we mean by a relative performance estimation. We don't care that the average wait time of your sim is actually 20 minutes less than the real time of the average wait time in the real world. If we were trying to use your sim to optimize that parameter in the real world, then we'd need a high calibrated sim that would be able to produce that. But for a short project like this, it's probably going to be more feasible to say, well, I know my sim is off relative to the real world, but it's moving in the right qualitative direction. So it follows the right shape of the real world. So I'm going to compare my as is simulation to my proposed simulation. And if there's a difference in the simulated universe, then I would expect to also see a difference in the same direction in the real universe. And that's what we mean by relative performance estimation. And so, you could do that with 2 systems or 3 systems and so on. And so that's when we talked about different types of t-tests for that. So if you happen to if you have to bring the same inputs into both of those simulated systems, then you can do a paired t-test. Otherwise, if those 2 simulated systems are independent from each other, then there are different 2-sample t-tests. You can use the pooled variance t-test or the unequal variance, the Welch's t-test. And in all 3 of those, what really changes here is the degrees of freedom and the formula for standard error of the mean. So those 3 formulas, the 3 formulas for the degrees of freedom and the 3 formulas for standard error of the mean are good to know for those 3 t-tests and to know when you can use that. So I could ask a question like, here's how I set up my experiment. Is it legit for me to use this t-test or this t-test? Or, here's a confidence interval that was generated from this t-test. Are there any flaws or something like that? So, knowing how your experimental design and just generally the constraints of the experiment affect the statistics that you're allowed to use on it is good to know. And then there's this Bonferroni thing that we've talked about a few times. When you're starting to talk about testing more than two options. So if you're doing more than just one pair, then the number of pairs of comparisons, you start fishing for differences. So if you can measure, so a lot of you, like in your input modeling reports, you said, here are a bunch of different output metrics I could measure. And I would say in a comment in a lot of those, like, well, which one are you going to use? Like, are you going to use all of them? Because if you use all of them, if you say, I'm going to look at the queue length, I'm going to look at the wait time and something else, all of these things are all performance measures. And you say in all 3, I'm going to look for differences between my as-is system and my proposed system. Then there's a 5% error for each one of those that you're just going to see a difference that's not actually there. So if you're going to use all 3 of them together to tell you whether there's a difference between your 2 systems, you have to have a different criteria for each individual check. And that's what this Bonferroni thing was all about. So if you've got 3 pairs of, if you're going to look like 3 comparisons, are they different in terms of wait time? Are they different in terms of line length? Are they different in terms of throughput? Then you have to then take your 5% error rate, your type 1 error rate, and divide it by 3. So it'll be 5 divided by 3% for each one of those. So that if you detect a difference in the family, then that family-wise error rate will be 5%. That's the idea behind Bonferroni for multiple comparisons. Any questions about that? About these different statistical approaches and their constraints? Okay. And then the last unit here. So we talked about 4 different variance reduction techniques. Those of you who are interested in AI and machine learning, these are behind the scenes. These also are used in a lot of the tools used to train neural networks. and process data and so on. If you get very large amounts of data, very large degrees of freedom, then you have to sort of figure out how to sample in an economical way. And that's exactly what we're doing when we're running sims as well. So we use the same sort of techniques there. And so we talked about common random numbers, control variates, antithetic variates, and importance sampling. And so, CRNs, those are the things that we use our paired t-tests for, where we're going to run the same random numbers into two different sims, and then that will pair the outputs of the sims. So for this random number stream, I get two outputs, one from simulation A, the other from simulation B. And I do that for a bunch of different types of random numbers. And each random number seed corresponds to like a different set of inputs. So I'm saying for this input, I run two models. For this input, I run two models, and so on. And then by looking at the differences there, I get a better idea of what's truly different between the models and not just between the inputs. That's the idea behind common random numbers. There's also control variates, and this idea that, so in common random numbers, I had a variance source in the input I was using. I was trying to control for variation among the inputs by doing the apples to apples comparison, where I run one input into two models. There's a little bit of a similar thing with control variates, where there's inputs you care about, but there's also other inputs that are sources of variation that maybe aren't the thing that you're focusing on. So you might be interested in how moving a cashier station around a model will affect the performance. But there are other variables that for some reason, like if you're doing a real simulation or a real experiment, it may be impossible for you to move the cashier station around without other things changing as well. Or there's just other variations that, you might move the cashier station on a Monday, and on a Tuesday, you might want to move it back. But now on a Tuesday, they've happened to change something else that's unrelated to the cashier station, but it just happens to be the things that they do on Tuesdays. And so there are other variables that introduce variation that look like noise on your output. But if you can measure those variables, you can then use them to subtract off variance that might be introduced by them. And that's what this control variate idea was. So I used the example of you're trying to study differences in how you're running your solar inverters, but temperature is another variable that's going to affect performance. Temperature isn't the thing you're studying, but it is going to affect your outputs. So I measure temperature, and I use my measured temperature to subtract off variance that is likely due to temperature, so that the variance that's left over is the variance due to the thing I'm actually studying. So that's the idea behind control variates. And then we talked about antithetic variates, which is like a version of common random numbers, but instead of comparing two systems, it's for better estimating things with one system. So this is the idea that you run one set of random numbers into as one replication. So these are these might be customers, these might be service times, or so on, but they run into one replication of your sim. And then for the second replication, you do those random numbers, which are all between 0 and 1, because they then go into inverse transform sampling and so on and so forth. You can then create a complementary pair. So you can do 1 minus those, and then those go in. And for most random numbers, if you plug in a low value of a uniform random number, if you plug that into an inverse transform sampler, most of the time that will give you, let's say if it gives you a small value, a small sample of the variable you care about, if you do 1 minus that, you'll get the opposite coming out of your inverse transform. So this idea hopefully then allows for you to set up these pairs where you get an easy set of customers on the odd set of replications, then the complementary even set of replications will be a hard set. And then that helps guarantee that the antithetic variate, which is the average of those two, is taking two numbers that are on the opposite sides of the average you're trying to estimate. And by bringing them together, it reduces the variance. I use this, if you see me use this notation on the final, that's definitely a possibility. So notice here that I'm saying that my simulation outputs a Y. I've got this pair I'm grouping together by calling it the first pair. That's where that one is. And then I'm using A to be the kind of the odd side. That's the independent side. And B to be the complementary side. So the antithetic variate is the average of those two. So that's why I use that notation. And I might use that notation, as you'll see in previous final exams, sometimes I'll use that notation to refer to the antithetic variates. And then the last one, importance sampling. And this idea that after learning how important it is to get your input models right, we finally give you the permission to just use arbitrary input models. They're not totally arbitrary. They have to have the same range as the right input models. But if you can compare the pathological input models to the real input models to see how rare the pathological inputs are relative to the real ones, then you can run your simulation totally in the pathological world, which generates all these events, which would be very rare in the real world. But by knowing that combination, by knowing that that the inputs are very rare and how rare they are, you can use a likelihood ratio, this FX GX ratio here, to scale those outputs down, and then allows you to then estimate the frequency of rare events in a simulated world where they're not rare. So that's the idea of importance sampling. Is we're going to focus on inputs that give us only the rare events, so that we generate a simulated world where rare events are the norm. And if we know, based on our, the real input model and the input model we use in our bizarro world, where the rare events are the norm, then we can say, take that high frequency of rare events and turn it into the real frequency in our real world. And that greatly reduces the number of samples that we need. Because if you have a rare event, this came up recently in office hours, that there was a rare failure case that would only happen once every, 20 days or 20 months. And he said, well, if we want to study a system with or without those failures, that's fine. But you're going to have to run lots and lots of replications to see the effect of that because it happens so infrequently. And an alternative to that is, well, if you really care about estimating how infrequently that situation occurs, you can try to simulate a versional world where you get like failures every day, and then you can rescale that frequency to the real world. That's important sampling. All right, any questions about that, VRT? And then the last thing here, just arena stuff. So, know the basic flowchart blocks, create, dispose, decide, process, know that record exists, know how resources are implemented. Know that a process itself isn't a resource. Processes are where resources and entities meet. So this is a common misunderstanding. You define resources, and then processes are just the sandboxes in which resources can play. You can have multiple processes all using the same resource. So understand, like, what is a process for? We frequently talk about doing seize, delay, release inside a process, but you can split those up in Arena. You can seize separately from delay, separately from release. The call center model that you saw in the lab was an example of that. So know about those three, like, what's going on? What does it mean to seize a resource? What does it mean to release a resource? And how do delays work? So knowing how those are split up. The syntax here for your common continuous distributions, know that for an expo only takes one parameter. So if you see an expo with two parameters, then that second parameter is that random number stream. So that means that somebody has wanted to change the random number stream that's feeding these expos. Know how to use disk, understand how to configure Arena for VRT, and understand how to interpret statistics from those post-simulation reports, like those confidence intervals and so on. And that's it. That's the whole class. So we're basically at time. Any quick questions? Otherwise, I have no clicker. Happy to take questions afterwards. Definitely email me. Once the exam's out, I can't answer content questions about the exam. The exam should be out tonight. So if you do have any burning questions, try to contact me today about those content questions.